We are back with more about transforming absolute value functions. So in our most recent video, we looked a little bit at how we could move an absolute value function left and right, and how we could move an absolute value function up and down. And we had to come back for another video to explore together how we could take that graph and possibly reflect it, and or adjust the steepness of the V. So could we make it more narrow? Could we make it more wide? And to answer this question together, I'd love to appeal to prior knowledge as much as possible. I think that's always the best way to do things. So I'm going to pick on a quadratic real quick. Let me go ahead and graph f of x equals x squared. I know you've all experienced that in an intermediate algebra course or whatever math course you took related to algebra. So by being in college algebra, you've got some sort of algebra background. Now, with the parabola, again, you've probably experienced finding the vertex of a parabola. That ties in a lot to that left, right, up, down sort of motion. But you probably also remember some things like how to make that graph reflect across the x-axis or how to make it wider or narrower. So just to show, for example, if I take another parabola, and this time I'm going to throw a 1/2 out front, how do those two graphs compare? So the graph in orange has a 1/2 coefficient on the x squared. The blue is just 1x squared, the base graph. So we can see here that throwing a constant multiple, right, a coefficient out front of x squared, in this case made the graph wider, but not every coefficient will make the graph wider. Let's pick something like 2 out front, 2x squared. And let me make this one, how about in green? Now the green graph appears to us to be narrower than the base graph. So this again is applying transformation knowledge to parabolas. We can just as readily take this understanding and apply it to our work with absolute value graphs. All right, so let's try it. I'll go ahead and turn these parabolas off for a moment. So it seems like we need to allow for some coefficient on x squared. And I don't want to just be limited to 1/2 or to 2. So I'm going to use, as we've talked a little bit about, a slider. So I'm going to use a value a. I'm going to add it as a slider so that a can take on any number in between -10 and 10. Or if you want, you can even adjust these to make it go more negative or more positive. So here's our absolute value graph. And what I'm going to do, just because I think it's important for our frame of reference, is let's keep the base graph in blue, and then let's let our transform graph be in orange this time. So let's just play A. I'll slow it down a little bit so we can take it in and watch what happens. So we are now playing A on the absolute value graph to see what it does to the V shape. And I'm just going to let it play for a minute and I'll shut up so you can make some observations yourself. So A is doing a couple things, right? A may feel a bit harder to describe than the H and the K that we worked with previously. So probably if I were able to ask all of you and you could hear each other's responses, I would hear probably at least 2 different ideas about what A is doing. Maybe more than that. But I think we could agree that A definitely is adjusting the shape of the graph. So unlike the horizontal or vertical shifts where the graph V shape just was moving around, now the V shape is actually adjusting in its wideness or narrowness, right? So at the current snapshot where I paused A, I'll just make it a nice whole number. A is 5, right? And we can see relative to the blue base graph, this new orange graph is narrower. So far we've determined that when A is greater than 1, maybe, the graph will appear narrower than the base graph. Watch what happens when A is actually equal to 1. You may have noticed this before I hit play on A. When A is equal to 1, these graphs are actually the same graph. So I'm turning the orange graph dotted just so you can see that the base graph and the orange graph are the same when A is 1, because the base graph technically has a coefficient of 1 out front. So hopefully that helps a little bit. Let's turn this back to solid. So watch when A goes, let's look at it growing from 1. So I'll let it float back to the other side before I start commenting. So we're coming back towards an A value of 1. Not there yet. Notice when it's less than 1, what's happening? It moves pretty quick. Now it's greater than 1. So when A is greater than 1, the graph is narrower than the base graph. And it can feel like a lot to comment on all at once, so let's start writing some notes. When A is greater than 1, the graph is narrower. I'm going to use the words narrower and wider just to make it easy. Okay, now let's look at when A is less than 1, but still positive. So now let's bump A back to something like 0.5, right, or 1/2. When A is a half, we can see that the orange V is wider than the original blue V, but it's still, above the x-axis. It's still maintaining that opening upward kind of position. So I could say when A is less than 1, but still positive. This is a little wordy, but hopefully we can build to a slightly more refined definition together. When A is less than 1, but still positive, the graph is wider. So far we have addressed the cases of when A is positive, there are two possibilities. A positive A between 0 and 1 is wider. A positive A greater than 1 is narrower. But now let's watch A become negative. So we're still going positive. We're going to swing back and watch what happens as we, in a moment here, begin to go negative. Here comes negative A. I'll just pause at a random negative location in just a second here. And let's zoom out a little bit more so y'all can see. So when A is negative, it still has the ability to adjust the wideness or narrowness, but the other aspect that changes is it's now reflected across the x-axis. So I can at least make a little statement here that says when A is negative, another way of saying that is when A is less than 0, if you like, the graph reflects across the x-axis. So here's kind of a weird way that we can use absolute value within our discussion about an absolute value. It turns out that when the absolute value of A is greater than 1, the graph is always going to be narrower. So for example, the current A value showing on the screen is A being negative 2.48, right? And you can see that the orange V is reflected, like we just talked about, but it also is still narrower than the blue V. And that's because the A value is, its absolute value is still greater than 1. So I could actually say when the absolute value of A is greater than 1, the graph is narrower. When the absolute value of A is less than 1, the graph is wider. So that's a little bit about kind of not just picking the graph up and moving it left, right, or up and down, but now it's more about what we would call compressing or stretching the graph. And again, this transformation here, it doesn't just apply to absolute value functions, it applies to polynomials, right? We saw the quadratic example, so really useful kind of information. So hopefully that's pretty neat to you. And we'll look at solving absolute value functions now.